Hey everyone, this is our lesson on the periodic table, and we are going to be focusing on elements that says 1 through 18, but we're going to be focusing on like breaking down the periodic table a little bit. We're going to do that in this lesson as well as the next one. So this one's going to be a broad look at the periodic table, and the next lesson will be a little more specific to like groups on the periodic table. All right, so by like the late 1700s, we had only developed, or scientists have only discovered about 17 different elements. And as science progresses, as it has advanced, we were able to quickly find more and more and more elements. Well, as we find all these elements, we have got to shrink this down a little bit. While we find all these elements, we now have to find a way to organize them in an efficient manner that we can look at and we can analyze very easily, which is how we came up with, or we discovered, the periodic table, which is why I like this little meme over here. So first we have Antoine Lavoisier, and he grouped the elements in categories such as metals, nonmetals, gases, and earths. But as we started to find other elements, this wasn't the best method for separating them in terms of understanding properties, because you could see overlaps in properties, and we needed a different way to kind of break them down and organize them to better understand those properties, which is where Dmitry Mendeleev comes into play. So this man was a broke physicist, scientist, who was commissioned to make a textbook organizational pattern of elements. And he did that, and it actually became our first table of, like, our first periodic table. And the way he did that was he put them into rows, and he organized them in order of increasing atomic mass. So he was looking at the isotopic mass that we discussed in atomic structure. And this ended up putting the elements in columns, so up and down, vertical columns, with similar properties together. And it was really, really cool to see, because we hadn't been able to find a way to organize them like this yet. And he was so spot on about this that he even left blanks in the periodic table for future elements that would be discovered. And they were discovered, and they did fit exactly in the spots that he left. So he was very, very brilliant when it came to organizing the periodic table. So he is credited for creating the first periodic table. And the periodic table is an arrangement of elements in columns based on sets of properties that repeat from row to row. So that's known as periodic law, which we'll go over in a minute. But each of these columns, so I'm going to use this little meme over here. So each of these vertical columns, the elements within those vertical columns have very similar properties. Now, over time, we did see that atomic mass was not the best way to organize it, because there are a couple little kinks in there. You have some elements that are actually out of order based on atomic mass, but are where they need to be based on their properties. Okay. So those are, we learned that was probably not the best way to do it. So our modern periodic table, the one we currently have today, which was developed by a man named Moseley, he arranged them in order of increasing atomic number, so increasing number of protons. And each row on the periodic table, so the rows are left to right, horizontal, those are called your periods. And then your columns are called groups or families, but I tend to refer to them as groups. And then elements within the same group will have similar chemical and physical properties. And that, again, is known as periodic law. So as you go across a period, you will see a huge variety of properties, but within the same column, you will have the same properties. There are 4 basic pieces of information that you can get about each element on the periodic table, and I'm going to use this little block over here to kind of help point it out. So first you can get the element name, and on your periodic table, I'm pretty sure the element name comes under the symbol, so under the letter. You can get the element symbol, which will be 1 to 2 letters that represent the element itself in a chemical formula. The first letter is always capitalized. The second one is lowercase if it has a second one. So carbon is only letter C. You get the atomic number, which should be at the top of the box on your periodic table. And then you get the average atomic mass, which will be this decimal value at the very bottom. So it is on the bottom of your periodic table as well. So again, our modern periodic table, we just talked about the basic breakdown here. But we can look at classifying elements in 3 different ways now that we have a periodic table that is set up well. So the first way is we can classify them as solids, liquids, or gases based on their room temperature state. So we're not like heating them up, just based on standard temperature, standard room temperature. You can look at solids, liquids, or gases. A lot of times these are represented by black is solid. So if you see on here, which is a great example, you see these element symbols are in black. Those are the ones that are solid state. If you see them in blue, it should be liquid state. And then if you see them in red, it's usually gaseous state. Elements can also be divided into those that occur naturally versus those that were synthetically made in the lab. Usually if they are synthetically made, then they don't have a decimal value average atomic mass. They have a whole number because they were made in the lab, which means they don't have isotopes. But the way that we tend to look at the periodic table being broken down the most is metals, nonmetals, and metalloids. And that's what we're going to focus on today. There's Eddie. So we've got metals first, and these are good conductors of heat and electricity. They are malleable and ductile. So malleable, quickly, means that you can hammer it into a sheet without it breaking. And then ductile means you can stretch it into a wire. Metals tend to lose electrons in compounds, and that means they form cations. Cations are considered positively charged ions. All metals, except for mercury, which the symbol for mercury is Hg, are solid at room temperature. Mercury is liquid at room temperature. And then the metals that are group B, which would be the short stack in the middle of your periodic table. So you've got tall columns and then short columns in the middle. Those are your group Bs. These are known as your transition metals. And they're called transition metals because they have more than one charge in an ionic compound. For instance, iron can take a +2 or a +3 charge depending on what they're bonding with. There you go. Now we can talk about nonmetals and metalloids. There's not as much information that goes with them, so I can talk about them together. So nonmetals are poor conductors of heat and electricity. They are basically opposite of your metals, hence why they're called nonmetals. Most nonmetals are gases at room temperature. There are some that are liquids and some that are solids. If they are solid, they are very, very brittle. So bromine is our only nonmetal that is liquid at room temperature, and it's a very bright red liquid. And then the ones that are solid are brittle and dull. They are not malleable and ductile. They will shatter when you hit them. Carbon is an example of this. Nonmetals also tend to gain electrons in compounds, so they form negatively charged ions, which are called anions. Then we've got metalloids, and metalloids are elements that have properties of both metals and nonmetals because they come between them on the periodic table. And most metalloids will conduct electricity only under certain conditions, which is why they are called semiconductors. So a lot of them won't do it by themselves, but in a compound, then they'll conduct electricity. So if you look at this picture over here, I just want to show you a breakdown. Most of the periodic table is made up of metals, which are these blues. So they are on the left side of the periodic table. They make up 80% of the periodic table. Then we've got metalloids, which are on this green section, and on your periodic table you will see a very bold line that cuts through here. That's called the stair step. Any element other than aluminum that touches the stair step is considered a metalloid. And then the right side of the periodic table past the metalloids are the nonmetals, and then you also include hydrogen in that. It's just over here based on its properties and its valence electrons. So now let's talk a little bit about periodic properties. So as you move across the periodic table from left to right, your metallic properties will decrease and your non-metallic properties will increase because you're going from metals all the way over to non-metals. So as you're getting out of the metals, you should have a decrease in metallic properties and an increase in non-metallic properties. As you go down the periodic table to the lower left-hand corner, you increase the reactivity of metals. So like cesium and francium are our most reactive metals, which means like you put them in water and they explode very quickly. As you move closer to the right-hand corner of the nonmetals, you increase the reactivity of your nonmetals as you go up. So fluorine, we're not counting group 18. So fluorine is our most reactive nonmetal. The period number for each row, so each row is numbered 1, 2, 3, 4, 5, 6, 7, on the periodic table represents the number of energy levels of that atom. So that tells you like how many rings on a Bohr model. It also tells you about the electron configurations, which we don't really have to worry about so much here, for the elements in that row. Okay, so we look at knowing how many circles we've got for electrons. So the Bohr model of sodium has 3 energy levels, and that's because sodium is located on the 3rd row of the periodic table. The group A numbers. So if you look at your periodic table, you'll see that there are tall sections and then that short section in the middle. So now we're focusing on those tall sections. Those are called our A groups. And in our A groups, if you look at the numbers, column 1 is also referred to as 1A, 2 is 2A, 3 is, or row 13 is 3A, 14 is 4A, 15 is 5A, so on and so forth, till you get to 8A. Those A group numbers, they will be in Roman numerals on your periodic table. This matches the number of valence electrons that each element in that group has. So group 1A has 1 valence electron. Group 7A has 7 valence electrons, not 17. And then, let me get rid of my picture really quick. A valence electron is an electron in the highest occupied energy level, so it's known as an outer shell electron. These are the ones we care about when it comes to bonding, because these are the ones that will move. So elements in a group have similar properties because they have the same number of valence electrons. The properties are not identical, but they are similar enough that they get grouped together. So every element in group 1A has 1 valence electron, has very similar properties to the other elements in that group. All right, guys, so now that we have gone through all this information,